So in this lecture, with last lecture, we said we have, of course, PV equal RT, the beginning of chapter 3. Then we define H equal U plus PV, enthalpy, specific enthalpy equal internal energy, specific internal energy, times PV, pressure times specific volume. And we give two new definitions. We said delta U equals CV delta T, and CV is heat capacity at constant volume, and delta H is CP delta T, heat capacity at constant pressure. This is for gases. This is for gases. Of course, this is for gas as well. So in the exam, if you heard the word gas, H2, HE, oxygen, nitrogen, air, any of these keywords, remember that PV equal RT. Remember, of course, DU equals CV delta T. Always, this is a key, important keyword in your, so you don't need even table if you're talking about dealing with only pure gases, ideal gases. Can you hear me guys now? No problem?
Yep.
Great. So we're gonna combine, we're gonna substitute in this equation. This equation is so important. This is the definition of enthalpy. So we can put this here, here. Let's differentiate this. If you differentiate this, it will be like delta H equal delta U plus delta PV, correct? Delta H is CP delta T, CP delta T. Delta U is CV delta T. PV is RT. PV is RT. R is constant, take it out. So delta T by delta T by delta T, we have CP equals CV plus R. This is a very important correlation. See, R, by the way, R is gas constant. Is
Can't
gas
see the
constant.
last.
Okay, can see the last one. I'm gonna move it a little bit. CP equals CV.
I think it's the marker color you used.
This is a new one, brand new one, but I'm gonna actually do by QR for you guys. So it's CP equals CV plus R. Can you see this now? CP equals
Yeah, I can see it.
CP equals CV plus R. That's important, famous correlation. For example, and also we have another definition, important, very important. It's called CP over CV. It's called K, sometimes gamma. This and this are very important for gases, ideal gases. Ideal. This is heat capacity ratio, CP over CV. This is CP, always CV plus R, always. For any gas, CV plus R. And R is gas constant, which is R universal, for example, over molecular weight. Table A1, right in front of this, table A1, gas constant. Let's take an example, air. Air is a very famous substance. I think 79% nitrogen, 20% oxygen, almost 1% carbon dioxide, and some other substances like argon and other fluids, other gases. Air, as a pure substance, we consider it as a pure substance. As one thing is called air, with this composition of other gases. It's pure substance. Does not change its chemical composition with anything. It's pure substance. It's air. It has R equal 287 joule per kilogram Kelvin. This is called gas constant. Gas constant. R universal over 18 for air, it gives gas constant. 29, molecular weight of air, I think it's 29, 28 point something. Go to table A1, molecular weight is 29. It has Cp equal 1004.5 joule per kilogram Kelvin. Go to table A2A. Cv, of course, 17 joule per kilogram Kelvin. So if you notice, Cv plus R equals Cp. If you please add Cv plus R, it will be approximately Cp. Is it clear? So Cv, always Cv. So if I give one of you, two of them, you can get the third one. K for air, or gamma, a specific heat ratio is 1.4. It's a ratio, it has no dimension, it's non-dimensional parameter. The specific heat ratio almost 1.4. If you divide this from 1000 over 717, it's 1.4. A specific heat ratio. For every fluid, for every gas, if I give any two, you can get the other two with these two correlations. If I give you, for example, R and K, you can get the rest, Cv and Cp, for any gas. Can you guys, is it clear now?
Yep.
Okay.
I had a question actually. For the equation where you plug in dH and du,
Yes.
For du, it's Cv dt, right?
Yes, yes.
Or is it Cu dt?
Cv. So it's Cp delta T for the H is delta H, Cv delta T for delta U, dRT for PV, which is PV equal RT. PV equal RT.
All right, thanks.
So delta T cancelled. Remember, it's Cp here, Cv here, heat capacity at constant volume. It's V. Usually we use V like this, volume. U is like this. Okay, guys, this is ABC class. Okay. No, this is Cv. Okay.
Thanks.
Finally, R. So Cp equals Cv plus R. You know, it takes me a lot of time to say Cp. I used to say Cv. Then they said no, this is P. Okay, okay. Cp plus Cv. So we are improved over time a little bit. This is what we took last lecture, and we did solve one problem. So if, for example, I give you, this equation can be written in per joule or kilogram. Look, I can say Cp equals Cv plus R, or Cp bar equals Cv bar plus R bar. This is the first one per kilogram, the second one per kilomole. Like, for example, this is R universal. Sometimes you use R bar or RU. So Cv bar equals Cv bar plus R universal. They are the same. So if we divide by molecular weight, we got the second equation from the first equation. Sometimes you have only Cv, but you want to get Cv, or you have Cp, you want to get Cv. Just abstract R. So if you have Cp, but you want Cv, so Cv equals Cp minus R. If you want Cv bar equals Cv bar minus R universe. So do not be confused. If you want, clear? So if you want Cv from Cp, it's Cv minus R. Sometimes tables provided for Cp. Just subtract R, you get Cv. Subtract R universal, you get Cv bar. Is it clear? Like this problem we solved in the last lecture, 54. That was given Cp par. If you go problem 54, page number 6.3 in our lecture 6, page number 3, problem 54. When I asked to determine the change in internal energy, and I said please use table A2C, A2B, A2A for hydrogen, H2. Unfortunately, this table was given Cp bar. All we need to do, subtract R universal. It will be Cv bar. So we use Cv bar to calculate delta U bar. Yes, it's integration of Cv bar delta T. After you get it, with a value, joule per kilomole Kelvin, just divide by molecular weight. It will be what you want. So when you want something, divide by molecular weight, you get what you want. So for R, Cv, Cv, they are all the same. So R, it's R inverse of molecular weight. Cv, Cv bar over molecular weight. Cp, delta U, everything divided by molecular weight, it goes from per kilomole to be per kilogram. And kilomole and kilogram, they are the same because for every material, the same mass represents some number of moles, which is constant number called number of moles. Even if it's not gas, this correlation always correct. This is for one pure substance is constant. For example, for air, molecular weight is 29, almost kilogram per kilomole. This is constant for air. Always this value, 28.9 something, which is we can used to say 29. Is it clear, guys? Is it clear? Hello?
Yeah, I just had a quick question.
Yes, go ahead.
Oh, so what's the bar again?
Any bar means per kilo mole. So we, Cv, for example, is heat capacity per kilogram per Kelvin. Cp is heat capacity per kilogram per Kelvin. This is as constant volume, this is as constant pressure. But Cv bar is heat capacity per kilomole per Kelvin. So the difference here, this per kilomole, this is per kilogram.
Okay, thank you.
And that's the ratio molecular weight, that's it. So any bar you will see means per kilomole. Without bar, per kilogram. Is it hard? So any equation you have, you can write it exactly the same way we write the other per kilogram. But use bar, it's per kilomole. Without bar, it's kilogram. Clear? Sometimes the table provided, like for example, open please with me table A2C. Please, I'm going to share it with you, okay? To understand what's going on. Table A2C, guys. Can you see table, guys?
Yeah.
Yeah.
Open A2C, ideal gas specific heats. So is A to A, no, A to B, no, A to C, yeah. For example, A to C. Can you see what is given here? Given here CB bar. Oh, CB bar. I don't want CB bar. I want CB, for example. So CB bar, to go back to CB, just divide by molecular weight. Divide by molecular weight. It will be CP. How about if you want CV or CV bar first? If you want CV bar from this equation CB bar, it means this is joule per kilogram Kelvin at constant pressure. But I don't want this. I want, for example, delta U or delta U bar now. So the first step to get CV bar. So you have CV bar, correct? Subtract R inverse. to get CV bar. So first step to get CV bar. The first step to get CV bar. Then continue your calculation until you get delta U bar. But I want delta U divided by molecular weight. Got it? So this table was given CV bar. I don't want CV bar. I want CV, or at least in the beginning CV bar. So from this CP bar, subtract R universal 8314 joule per kilomole Kelvin, constant number. You get CV bar. CV bar. Continue with this CV bar. So if you go back to the lecture, I can open the lecture for you. I'm sharing right now. Can you see my share, guys?
Yep.
Okay, let me share again the lecture 7 here. Page 6 something. So page 6, 63, 64. I think so. 1 second. Oh, this is lecture 5. No, this is lecture 6. Yeah. So if you go back, please, to here. Can you see this problem, guys? Problem 54, this problem. He wants delta U. He wants delta U. Correct?
Yep.
Delta U, guys, we need CV, not CV bar. Not CV bar, not CV at all. It's CV. But the table given CV bar. So the first step, subtract R universal. Can you see this subtraction? This subtraction? So the equation given CB bar equal A plus BT plus CT square plus DT cube. I subtract R bar or R bar universal. It became CV bar. It became, okay? What I did, just subtract R universal. So here is kilojoule per kilomole Kelvin. I subtract 8.314. It became CV bar. Plug it in CV delta T, integrate, you get delta U bar. Finally, it's 12487 kilojoule per kilomole Kelvin. Actually, no, not Kelvin. This is energy. Kilojoule, kilomole directly. Molecular weight of hydrogen is 2.016 from table A1. You can get delta U. Divide by molecular weight, it became 6,194.3 kilojoule per kilogram because I divide by 2. 12,000 became 6,000. You got it, guys? So the first step, I got CB bar from the table. A plus BT plus CT square plus DT cube minus R universal became CV bar. Use it, integration CP delta T became delta U bar. Integrate and substitute upper limit T2 minus T1. I mean T2, for example, square minus T1 square. T2 cube minus T1 cube, and so on. After integration, you get delta U bar. I don't want delta U bar. I don't want per kilomole. If you got until this step in the exam, you got 9 out of 10, for example, or maybe 8 out of 10. But you need to divide by molecular weight to obtain kilojoule per kilogram. If I want delta U, not delta U bar. Okay, guys? Any questions? Any questions? Let's take one more problem. Guys, any questions?
What's the equation next to M again at the bottom? Is that volume over, what's that term below volume over there? For what M equals, at the very bottom, it'll say M equals something.
2.016?
Oh no, it says for a pure substance, right?
Oh, on the board?
Yeah, it's under pure substance. It says M equals
Here?
Something.
In the board?
Yeah.
Yeah, on the board. It's at the very bottom. It
Green
says,
writing.
Okay, 1 minute. This one?
No, on the right.
On the
On
right?
the board on the right. Yeah, what's that say?
M equal 29. This is a molecular weight of air. It's 29 kilogram per kilomole. So for any pure substance, go to table A1. You can get the molecular weight or even the gas constant directly. For any pure substance, air, water, vapor, hydrogen, go to table A1 and check it. Okay, guys? Okay?
Yep.
Okay. So let's take one more example for you to be more aware what's going on. If you go to the very last page, I wrote some like very fast solution for you. Let's take problem 41. Can you see problem 41? 341? In the very end of lecture lecture 6, page 5. Lecture 6 is uploaded for you. 6465. Open page 65. Please read problem 341. I want you to read 341, please. And read it again together. Okay, guys? So it's 10 kilogram of refrigerant 134A or 134A at 300 kilopascal fills a rigid container. Rigid means constant volume. This 14 liter is constant. It means the specific volume is constant. Also, there is no work. So 10 kilogram of this fluid fill a 14 liter tank. So we have specific volume, we have pressure, we have everything about this state. Pressure and a specific volume, which is volume divided by mass. Determine the temperature and enthalpy. Of course, we can determine. What table would you need to use here, guys? What table? Can somebody tell me? Problem 41. For the first part. Table what, guys? Can somebody tell me?
We can't see the board, Professor.
Oh, you can see the board? Okay. But how about the table?
Is the problem on the lecture or is it?
Yes, lecture 6.3. Lecture 6, page 3. Or problem 341 in the textbook. So you either open the textbook or the lecture. 341, page 6364. Maybe 65. Maybe 65. Yeah, 65. Okay, guys. Guys, can you read the problem, please? So we have 10 kilogram of R134A at certain pressure and the volume of rigid tank liter, it's 10 minus 3 meter cube. So the pressure was 300. This is rigid tank. That's very good. This means there is no work. Specific volume 1 equals specific volume 2. We move vertically in TV diagram all PV diagram. So he wants determine first. This is state 1. So this is mass 1, which is the same as mass 2, P1, V1, which is the same as V2. Determine T1 and H1, or maybe U1. Then, if I add heat, Q is added to the system. Pressure became 600 kilopascal. 600 kilopascal. Determine the T2, H2, and so on for U2. So determine this and this. Determine this and this. For state 1, we have everything. Can you see the board, guys? You see the board?
Can you switch markers? It's a little blurry.
Okay. Yeah. So P1, 300 kilopascal, V1. Is that one is better?
Yeah, that's better.
Yep.
So T1 and TH1, maybe U1, anything he wants at one. He said P2 became 600. The pressure at 2 became 600. I want T2 and H2. Okay? You guys?
Yeah, we're following.
So we have here several things. This problem, if it is gas, if you have P, V, this is V over mass is specific volume. You can get temperature easily. If you want H, CPT for this gas. If it is gas, but this is fluid, which has liquid and gas, it means mixture. So this case, if they repeat the same problem, and this was pure gas, you can use the ideal gas law. So ideal gas law again, ideal gas law, something we use it for gases. Only gases. Only for gases, please do not mix. But if you have liquid and gas, like mixture, use steam tables. For example, in this problem, we're going to use table A13 and A14 for this fluid. Please open table A13 and A14 for this R134A. We need to use the appropriate tables. Okay, guys? Table A13 and A14. Superheated. And A actually 11, 12, and 13. A, 11, 12, and 13. Open the tables, A, 11, 12, and 13. I can share it with you. Let me share it with you. Share. So if you go look at this tables, A11, A12, A13, these are the saturated table and superheated table for R134A fluid. So here, like this is equivalent to table A4 for water. This is equivalent to table A5 for water. This is equivalent to table A6 for water, superheated fluid. Okay? Is it clear?
It's clear.
So use A11, 12, and 13 for this fluid. Okay, let's go try to continue solving this problem. So given for you volume and mass, you can easily say I don't have notes for this one, it's okay. So A41, we have state 1, we have V1, which is V1 over mass 1, which is 14 liters divided by 10 kilograms. Yes, it's 0.0014 meter cube per kilogram. We have P1, which is 300 kilopascal. From these two together, you can get everything for this state. Go to table A12. A12 is better here because you have pressure. So A12 for this fluid, R134A, table A12, table A12. You will find this state, most probably mixture. This specific volume between the F and G. So we have mixture between the VF 0.00076, little bit less than the water, and less than VG 0.001 or 0.01. It's something, it's 0.0014. It's between this and this pressure. That's easy. That's very good. So from here we can get X, the quality, which is V1 minus VF over VG minus VFG. You can get quality. How much mass of the vapor? How much mass of the vapor? V1 minus VF over VG minus VF. And these parameter guys at pressure 300 kilopascal. Table A12. Clear, guys? You can write behind me because there is no notes for this problem, maybe. So X equals this. This is the quality. I can get everything. If I want U, it's UF plus X UFG. Course 1 and 1. And this is 1 unknown. I want H is HF plus X HFG. Course 1, 1, 1, 1. Everything is 1. I want S. I want anything. I want T. It's T at this. Unfortunately, you will find here two rows, 320 and 280 pressure. Do you remember, guys, what should we do? If we go to a pressure table, you find 280 and 320. What should we do, guys? Guys, what should we do? What should we do, guys, here?
Average.
What?
Average.
Exactly, interpolation, but here is simply average. Oh, so you can get U1, for example, and you can get T1. T1 is average. So you get T1 here and T1 there. So we did similar problem before, but now I'm gonna do more details. How about this? Okay, this is the solution for state 1, we did it. State 2, guys, very same. We have V2 equal V1, we can get, and we have V2, which is 600 kilopascal. So here, if you plot the, let's say the TB diagram, this is the constant pressure line. So you was here, you were here, became here. This is state 1, this is state 2, another pressure. Oops. So you go from state 1 to state 2. Okay, guys? You go vertically because the specific volume is constant. Volume always 0.0014 meter cube per kilogram. Correct? Correct? Guys, you have any question, guys?
What problem is this again? I can't find it on the lecture.
41, 341 in lecture 6-3 or 5.
I have
6-5.
Question.
Yes, go ahead.
The quality equation that you used on this problem, can that be used all the time, or is that only for saturated mixers?
If you have only quality habit in mixture, if quality is 0, it means you are saturated liquid. The very left curve, this curve, is called saturated liquid, x equals 0, only for this. If quality is 1, you have 100% vapor. So quality is 1. So only x happen in between, from 0 to 1. It cannot be superheated, it can be compressed liquid. It's only in the mixture between 0 and 1. So quality cannot be greater than 1. Quality means how much mass of the vapor to the total mass. It means you have liquid and you have vapor. Got it? Is it clear?
Yeah, thank you.
How much mass of the vapor to the total mass between these two lines. So in exam, I'll ask you, draw for me 2 lines, 1.3 regions, compressed liquid, saturated mixture, and superheated region. And there is critical point, saturated liquid, saturated vapor. X in between from 0, from the left, we call it F. Any property here is F. Any property here is G. X in between from 0 to 1. Okay, guys? So let's go to this problem. State 2 is completely known now. You have V2, which is V1. You find it also mixture. It can be vapor, but it would be between Vf and Vg at this pressure. It will be between, so you can get X2. You can get X2, which is V2 minus Vf over Vg minus Vf. So the difference here, guys, at state 1, these values at 300 kilopascal. At state 2, these values at 600 kilopascal. Table A12 at 600 kilopascal. If it's not there, make an interpolation. So Vf and Vg in state 2 at 600 kilopascal. Is it clear, guys? We can now determine what? U2, H2, anything at 2. Anything at 2. Let's say, for example, U2. U2 is UF plus X UFG. But everything here is 2. At pressure 600 and quality 2. Guys, here I'm heating the tank. I have tank. I add heat. Pressure go from 300 kilopascal to 600. Can I calculate Q? Can somebody tell me how you get Q? Q in this problem? This is homework 2. Can I get Q? This is rigid tank. It means there is no work. So what is Q, guys?
Yeah.
What? What? M delta U, because there is no work. Q minus W equal delta U, capital. Q, what I want. W is 0. Q minus W equal delta U. Q, what I want. Heat addition, it's positive. This is 0 because this is rigid tank. Delta U is mass times specific volume, a specific internal energy. I have U2 from state 2. I have U1 from state 1. Mass is given, 10 kilograms. I can get how many joules are needed to raise the pressure from 300 to 600. Let's take a 7 minutes break. We'll come back at 11. Okay, guys? There is no quiz today, but I'm going to continue in the next chapter, lecture 7, which is supposed to be today. Okay, guys? Any questions?
Yeah. What are the terms that you wrote for X2 representing
This one?
quality? Yeah. What does it say? Is it
V2 minus Vf over Vf over G minus Vf. Exactly like this one. Exactly this one. V minus Vf over Vg minus Vf. Actually, we don't have any other definitions. V minus V over V minus V. V minus Vf. It was before that V equal Vf plus X Vfg, which is Vg minus Vf. We rewrite it to get X. In thermodynamics, we always want to see one unknown per equation. We always. If you see two unknowns in one equation, that's wrong. You need to see one unknown per equation. Okay?
Thank you.
So every equation, every function you see, it's not a function. It's impossible to do any function. It's always one equation and one unknown. Function mean more than one unknown. So you can have inputs and outputs. Okay. Let's take a 6 minutes break and come back at 11. Okay, guys? See you. 11, I will start. See you guys. I'll keep it like this if you want to write any notes. So the difference between last chapters and this chapter, previously we just get state. Chapter 3 get state 1, get state 2. Chapter 4, we get what is the link, how much heat needed to get this. Just M delta U, that's it. Whatever you did between state 1 and state 2, you get delta U, that's it. It's called first law of thermodynamics. How much did you pay to raise this pressure or temperature or such energy added to the system? Okay, guys, see you in 3 minutes or 4 minutes. Okay, does anyone want to write anything from the board? I can close it if you want. Okay, guys?
I have a quick question.
Go ahead.
For UF and UG,
Yes.
would that be getting them from the table, from the steam tables? Or?
Exactly. Go to
Okay.
table 812. Please go table now 812.
Yeah.
You will see at pressure 280 and pressure 320. We don't want 280 or 320. We need in between, either interpolation, but this is easy, so we can make it average.
Okay, thank you.
So get VF at 280 kilopascal, and get VF at 320 kilopascal, average them. You get VF of 300. Make sense?
Yeah.
The same for VG. Plug everything in this equation, you get quality, either state 1 or state 2. Make sense?
Yeah, thank you.
This is homework 2.
One of you asked one question in the very end of the last part, which was this problem was in homework 1. Who did that? Say that. One of you said this is homework 1. So this is a good and at the same time bad thing about thermodynamics. Guys, are you all can hear me?
Yeah, we can hear you.
Unfortunately, thermodynamics, unlike any other course, it's something based on the previous lectures or previous homeworks. So homework 1, I ask you to get state 1 or state 2. Homework 2, I will ask you to get Q, which is the first law. If you cannot get a state 1 or state 2 from homework 1, it's impossible to solve homework 2. The same for homework 3, which is continuity of both of them. How about if we have it the same thing, but for open system? So we need to know how to do homework 1 or homework 2, because we add extra terms. So this course, which is the only course in your life, you will see that if you cannot solve homework 1, no matter what, you will not be able to solve homework 2 or 3 or 4 or 5. For example, in math, if you are talking, every chapter is different approach. Newton-Raphson, different for bisection. If you don't know this approach, it's okay. But you need to have the basics. Homework 1 and 2, mainly to get in the following homeworks. Okay, guys?
For homework 2, do we still have to show the process of getting to state 1 and state 2?
Of course, you need to show me what you did.
Okay.
The same in the exam. Let's say you did interpolation, but you did not show me. You're gonna be graded based on the final answer. If it's correct, you get the grade. If it's wrong, I will give you 0. But if you show me the steps and the result was wrong, it's okay. I will give you some grade for your steps. That makes sense?
Yeah.
Yes.
That's very fair. So if you need to show me as much as you can what you did, of course, meaningful. Do not waste your time and my time. Just give me meaningful information about this particular problem. The steps to this. If they did a mistake in the very beginning, it's okay. Many of you, if you ask a previous student, they did mistake in the very beginning of the problem, but they continue with this mistake and they get the full mark in this problem because I continue with their mistake.
Okay.
Is that fair?
I have another question.
Yes, go ahead.
Do you want us to draw the PV and TV diagram for everything in the homework too?
That's better for you. It will be asked in a separate question about PV diagram, but also in the problem, I will ask. If I do not ask, it's up to you, but it's better for you to understand. Try to solve without and with. When you see something, especially chart, we're more focused. Which table? This is table A4, this is table A5, this is table A6. You will be more focused if you see something on the diagram. And this will gonna be happen in the very end of the course when we go to the jet engines, when we solve an aircraft engine and get the thrust. You will see how beautiful it is to use the steam table or the charts, I mean. Okay. So the more you plot.
Is the
Yes.
midterm going to be multiple choice?
What?
Is the midterm going to be multiple choice?
No. Problems. There is one problem in the beginning. I will give you a sample. Don't worry. Next week, Monday, I will give you a sample in the review about one midterm, last year midterm. I'm going to solve it in front of you. Let's say 1 hour. And how can I use the table? How to do this? How to do that? Exactly like a midterm for you. Then after I finish this midterm, you will see that question 1 was some kind of theoretical definitions, multiple choice, true or false, just 10 problems from like 7 to 8 problems or 10 problems about what do you think about this? Define thermodynamics, define the types of heat, give me if this has happened, what has happened for, let's say water became ice, became water, or water became ice. What happened to is it pure or not? So you need to know what is going in the theory of the class. For example, water. If it's ice melted in water, it's still pure substance. You can mention this. It's pure substance because there is no change in chemical composition. That's very simple. You get 2 points. One for the yes, one for the no change in chemical composition. So we know that answer. So there is the very top question, some theoretical. Then 4 or 5 problems about to solve. Give me state 1. Give me state 2. Give me Q. Give me work. Okay, guys? Draw the PV diagram and give me this curve, this point. So usually it will be a variety of things, but in your benefits. Okay.
Professor, I had a question about the homework.
Yes, go ahead.
For homework 2, chapter 3, you have 3-80C highlighted, question 80, but it's not listed.
Yeah, I know. Look, you can discard any non-highlighted problem for the homework. However, I prefer to solve all of them for yourself. Maybe I will take one of the highlighted, put in the exam as it is. Of course, we're changing numbers. So if you know the solution, not only numbers, sometimes I change inputs to be outputs and output for inputs. If you don't know how to solve it, you're not gonna be able to solve it. So many of the highlighted ones are not given in the homework, correct? Some of them, like 6, 7 of them. So solve all of them. However, you only submit the homework 2 only, okay?
And I have another question. Is chapter 5 still expected to be on midterm 2?
Until this lecture is in midterm 2, till the end of this lecture. So here, so it's fair. I always give 1 week in advance. So homework 2 was 1 week. The only thing is not gonna be 1 week is the final. The final, you can take lecture on Friday, you have a final on Wednesday. That's it. This is the only thing. And I will give you 3 problems in this day, 1 of them in the final, for example, to make it easier for you. Anyway, so let's go now to chapter 5. Chapter 5 is about open systems. We're gonna take about 2 things, 5.1 and 5.2 today. 5.1 is conservation of mass. Continuity equation. The mass is conservative as well as energy. You cannot create or destroy mass. You need to just transfer it from one place to another. It's mass is mass, it's not going to change. Energy can change from one form to another, but mass is mass. This is conservation of mass. Everything is conservative. It means $100 minus 20, always 80. Correct? Have you ever make this 70? Guys, can you make 70? Can you make this 90? Can you do that, guys? No. So the simple answer is always conservative. Always equal the mass, whatever in, equal out, or the change. So if you have a system, mass is going in, mass is going out. There is mass in and mass out. Let's say you have more than one in. You can have more than one in. And you have more than one out. So you have more one in, one in, one in. But we have other things out. Like mass out, mass out, mass out. So the theory here is so simple, which is mass exiting minus mass entering equal delta mass system. Make sense? Of course, mass exit minus mass entering equal the net mass in the system. Let's make it word net mass in a system. So mass exiting, mass out, minus mass in equal net mass in the system. Make sense? Actually opposite, mass entering minus mass exiting. Because I put input, this is can increase, this is 0. So mass entering minus mass exiting going out equal net mass in the system positive. Let's say there is no, let's say you fill a tank, you have only input, this is positive. There is no output, so the mass keep increasing. So the net mass keep increasing, which is this is E0. Let's say you have a drain, so mass keep decreasing while there is no mass entering. So this minus equal net mass. Change in mass is negative. It means the reduction in mass. We used to write it this way: M in minus M out equal delta M, which is M2 minus M1, for example. This is delta M. It means change in mass. Or M dot in minus M dot out equal delta M dot. So dot means per unit time. M dot is rho AV. It's rho AV. Sometimes we use rho V dot. So this guy, we call it volume flow rate. We like it in constant density problem. This is mass flow rate. So we have M dot and V dot. You have seen that from high school. M dot equal rho AV. So rho is kilogram per meter cube, meter square, meter per second. The net is kilogram per second. V dot by itself, it's rho A. So you can say this equal this. V dot equal AV, which is equivalent to meter cube per second in SI units. V dot equal AV. This is volume flow rate. This is mass flow rate. Okay,
Professor,
guys?
it's really blurry. I'm having a hard time reading it.
Okay, let me close the camera and open it back sometimes.
All right.
Can you see it now?
It's a little better.
It's not clear enough to be able to like actually see.
How about now?
No.
Of course not. How about now?
Yeah.
No, it's the same.
Yeah, it's still not working well enough.
Okay, let me do it this way.
Maybe you can move it a little closer.
How about now?
It's not much better. I mean, it's a little clearer, but
How about now?
no change.
No change?
I think it's the camera itself. It's just like it like gets unfocused and it just slurry. It's really blurry.
Let me.
Uh,
Are you able to move it closer to the board? It's like a meter and a half. Like this is the distance between them. There's only says that I'm big, you know, I'm fat, so I need to have a space to move.
I understand.
Maybe it's the Wi-Fi.
You understand? I'm
Can
fat.
you
Okay,
reconnect?
thank you, man. How about this? Is it good like this?
I mean, if it were to be held still so it's not shaky, then it would probably focus on it. But
Okay, I can try to. Maybe I get me another chair. I got it. I have a solution. For every problem, there is more than one solution. Give me another chair. How about this? How about this, guys?
It's still the same.
I think it comes down to the quality of the camera rather than anything else, or the quality of the stream.
I bought this camera for $100 for you guys, so I thought it would be better. How about this? How about this? Still the same, guys?
Yeah.
Don't worry.
Can you just like write bigger on the whiteboard? Maybe
I
it'll
will do
just
that. I will
help.
do that. How about?
Yeah. I think that'll be better.
Okay, I'm gonna write it a bit bigger. So we were saying m dot equal rho av. This is velocity. This is volume flow rate. So this is velocity. You can use either v small, better, to make it distinguish, but do not give any other things. We have v, volume, v, specific volume. We have v dot, which is volume flow rate. Some people use q, but I don't like it. I use v dot. We have v small, which is velocity. So we have velocity. Is it clear now? A specific volume. We have volume. We have volume flow rate. Is it clear, guys?
What's the difference between the volume and the volume flow rate? Is it just the dot?
Yeah, it means per unit time, v over time. This is volume, like for example, AV, AH, the area of the base times the height, if you have conical or pyramid shape. How about the volume flow rate? It's AV, velocity. Area time velocity. Volume flow rate, volume per unit time. It changes volume per unit time. Okay? Actually, AV. IV. What did I do? AV is volume flow rate. Okay, guys? V is a velocity. A is a cross-section area. Rho is density. So what happened here, guys? So you can say m dot minus m dot equal this to m mass. We care about special cases much, by the way. M dot 1 equal m dot 2 exit equal entering, or 1 input equal output. We call it steady. This is a very important. We call it what? Steady. We call it what? So m dot in equal m dot out. We call it steady. M dot is rho AV, velocity, rho AV. Rho can be either steam tables or, for example, P over RT. P equal rho RT, so RT over P. Oh, actually, P equal rho RT, so P over RT, yes. For example, this rho, guys, is 1 over a specific volume. Okay, guys? Okay?
Yep.
So we always see this rho will be calculated based on, for example, the equation of ideal gas. If it's, for example, oxygen, air, any other gas, or steam tables, or 1 over a specific volume. Steam tables, like, for example, A4, A5, A6, whatever table, for example. You need to get the specific volume, then get density from that. Okay? Let's take an example. Problem 5.7. Problem 5.7. I'm gonna write it here. Problem 5.7 in your book. I'm gonna skip some problems, but please solve all the problems in the lecture. Problem 5.7. It's a tube, constant area. Air is going through. We have 2 sections, section 1 and section 2. So it's a tube, and air is going through. And we have section 1 and section 2. Can you see, guys? Can you see?
Yeah, we can see.
Yep.
Good. So we have 200 kilopascal, 20 Celsius, 5 meter per second. And this is 28 centimeter. This is the area, cross-section diameter. It's a circular. And its exit is 880 kilopascal, 40 Celsius. Typically, everything is steady, unless I said that it's not unsteady. Everything is steady. He wants required. It means required. What is required here? V dot at input, because it's different from out. M dot. Finally, V. What velocity? We have it. V out. Velocity at the output. So I give you velocity and input, temperature and input, pressure and input. At exit, I give you pressure and temperature only. And we have constant cross-section area. I can give you cross-section here and cross-section there, like the following problem. Okay, guys? Okay. Let's go at an inlet solution. We have P1. We have T1. We have V1, velocity 1.
Yes,
We
sir.
have P2.
On the right side, is that 40 degrees Celsius?
Yes, 40 degrees Celsius, yes. And the exit, T2. This is T2. Yes, you're right. 40
And what's
degrees.
the pressure on the other side on 2?
So here was 200. Of course, here is lower, 180, because this is a flow direction. This is called pressure gradient. We have flow is driven by pressure. So flow go from high pressure to low pressure. 200 to 180 Pascal. We have negative pressure gradient. Pressure decreasing. Drive the flow in this tube. Fluid mechanics problem. The air is moving, but temperature also decreases from 20 to 40. Velocity may increase, maybe remains the same. We will see. So solution, the first one, please make sure that what you are doing. We need the volume flow rate at the inlet. Volume flow rate, right, always the definition. Volume flow rate, inlet, is A, just A, V. A inlet, velocity inlet. That's easy. Area inlet is given. We have diameter here, 28. So pi over 4d square. Velocity given. So it's pi over 4d square times velocity. Pi over 4 diameter square. Diameter is 28 divided by 100 to be in meter. Pi over 4 times 28 over 100 square times 5. Make sense? .3079 meter cube per second. 0.3079 meter cube per second. Make sense, guys?
Yeah.
The second requirement, m dot. Just rho AV. We already get AV. So rho times V dot. You can put this if you want to make it easier. Rho is what, guys? Can somebody tell me what's rho? Actually, inlet equal rho outlet. So that's a matter. Get it from there or here. But we have everything at the inlet. For example, velocity. So rho, guys, how can I get rho? This is air. Can somebody tell me how can I get rho?
Is it P over RT?
Exactly, perfect. Just P over RT. This is exactly what I said. Always, you need to something remind you, when you read a gas, ideal gas, P over RT times V dot. We have V dot already. Pressure should be absolute, 200 kilopascal, so 200 times 10 to 3 Pascal. Temperature should be absolute temperature, Kelvin. So this 20, add to it 273.15 to become in Kelvin. Plug everything in this equation. So equal 200 kilopascal, 200 10 to 3. R from what table, guys? R for air. What table? R, gas constant of air. From which table? Which table are, guys? Gas constant. Can somebody tell me? You didn't solve homework one yet?
Table A2.
A1. Table A1. It's 28. Air is 287. 287 joule per kilogram Kelvin. Temperature in absolute temperature. So 20 plus this the temperature is times 293.15 Kelvin times volume flow rate. Make sense, guys? It's 0.7 kilogram. Just one line. Imagine that this is everything in one line. So it's 0.73 kilogram per second. 0.73. So we need the velocity and outlet. The last thing is required velocity at outlet. Velocity here. What is the velocity here? Can you see, guys, everything? So again, m dot equal rho av. So you can say here, this is just m dot divided by a times rho. Rho again. So m dot equal v equal m dot over rho a. Rho is p over rt, but p exit now. So exit, 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 exit. Temperature exit. Everything at exit. So the pressure a little bit lower, temperature a little bit higher, or the same for air. Area, in this typical problem, it was the same, 28 centimeter tube. M dot is the same. M dot, we got it here. It was 0.3 or 0.73 kilogram per second. Can you see, guys? So velocity at exit, it's m dot over p rt. P over rt times a. Make sense? Make sense, guys, or not? Guys, is it easy or hard?
It makes sense once you know where to look.
Yeah, you need to look at this. Yes, exactly. Everything has almost no value without doing it yourself. Solve it by your hand. Even area, like this simple area equal pi over 4d square. Some people confused. Some people say pi r square, yes, or pi over 4d square. You can do anything. I am a lazy person, very lazy. I used to have simple equation to get the final answer. So do not say, if you can say pi over 4 d square or pi r square. So you need to go from here, divide by 2, and divide by 100 to get the same area. But I like to do it one time. Okay? So for example, you need to do everything yourself. Area calculation, apply everything, calculate, try to use a calculator. I used to say you have 2 ways to do the mistakes, now or in the exam. So please try to do the mistake now. So everyone will do the mistake, but it's either now or in the exam. It's your choice. The following problem, 8E, it was English units. It's a good problem. It's exactly the same problem, but for a diffuser, it's like this. Something like this. So exactly, I give P1, I give you T1, I give you V1, velocity 1 at inlet. I give you P2, I give you T2, I give you area, V2, area, and I want area 1. This is problem. So because m dot is constant, m dot 1 equal m dot 2. This is rho AV equal rho AV. 1, 1, 1 equal 2, 2, 2. Rho is P over RT. A1, V1 equal P over RT. A2, V2. Actually, we don't want R. R is the same R. Gas constant. So we have P1, yes. We have T1, yes. We have V1, yes. Correct? We have P1, yes. We have T1, yes. We have area 1, no. We have V1, no. Yes. P2, yes. T2, yes. Everything should be absolute. So for example, this temperature, if it's SI, it should be Kelvin. If it's British, it should be Rankine. So if you have area 2, yes. You have V2, yes. So I give you this, guys, in the problem of this diffuser. I ask it for this. So what's the unknown? This guy. That's it. This is a steady flow. Is it hard, guys? So maybe in the exam, I'll give you the opposite. I'll give you area 1, ask for area 2. It's exactly the same procedure. But input became output, output became an input. Maybe I change it from SI to British, British to SI, and so on. Any question, guys? Any questions? Okay, guys. Let's move now to section 5.2. This is so important. M dot equal rho AV is so important. We need it for the following section, which is Ferris law of thermodynamics. For open system. Chapter 4, we have Ferris law of thermodynamics for closed system. Closed system like rigid tank and piston cylinder. Closed system was for no mass can cross the system. It was simply it was Q minus W equal delta U. Remember, guys, this is the Ferris law of thermodynamics for closed system. Is it clear, guys? Can you see?
It's very blurry right now.
Oh, I don't know why.
There was somebody said in the chat earlier that it looks like you might have autofocus happening. So maybe it's zooming, it's focusing on you rather than the board. So maybe if you can play with the camera settings after lecture, you can see if there's a way to just have it focus at a certain distance rather than trying to always change and follow you. Just an idea.
Yeah, I'm gonna do that. How about now?
Right there, when you're out of
That's perfect.
the shot, it's crystal clear. We can see everything pretty well.
Okay. Maybe because I'm moving, I may adjust it to fix it. Okay, I'm gonna do that. It's about 2 meter distance. I will fix it that. Okay. So first law of thermodynamics for open system is exactly like first law of thermodynamics closed system, but with additional details. For example, the only difference is we have mass in and mass out. But if you have no mass in and no mass out, you're supposed to go back to this equation, Q minus W equals delta U. So if you have a system, again, system with some inputs and some outputs. No problem. We have some inputs, we have some outputs. This is inputs, let's say, this is an output to a system. We're gonna use I love you for the input, and O or E for the output. The state gonna go from state 1 to state 2. So in the system, let's go from 1 to 2, from 2 to 3, or from 3 to 4, any state to another. And we have input I and output O or E. If you want O, it's okay, O. But I want to confuse, make it E for now. We have the same law, energy in minus energy out equal delta energy in the system. The same law. You remember this, guys? Delta En minus En minus E out equal delta T system, which is E2 minus E1. Now, E can be we have internal energy, we have flow work, we have kinetic energy. If talk about small, we have potential energy. For example, here V square over 2. Here GZ. If you have elevation, you have different altitude, different heights. If you combine them together, what is this, guys? What is this? This plus this is what? Can somebody tell me one word? U plus PV is what? Guys, can you hear
Equals
me?
H.
H, enthalpy, perfect. So we can rewrite this equation. Delta E system does not have PV, only have U. So this equation will be written like this. It's a very giant like this equation. Something equals something. E1, E input. It's mass input, sigma, times H input plus V input plus GZ input minus, this is energy input, mass input, times enthalpy plus kinetic energy plus potential energy. Correct? This is energy in. This guy is this guy. Correct? Can somebody understand? Total energy inside. I put hot water here, cold water here, vapor here. I put something here. So it's mass times enthalpy times kinetic energy plus potential energy. This is a total energy input. These are specific times mass give you total energy. Correct? Can you see, guys? Can you see, guys?
Yeah, we can see it.
Great. So minus sigma out of what? The same thing, but for output. What is output? Mass output or exit times H exit plus V exit square over 2 plus GZ exit equal everything going out. It can be 1, it can be 2, can be more. That's why we make summation. Summation. Usually we have one input. Usually you have one output. Sometimes you don't have input or you don't have output. If you don't have both, you go back to first law of thermodynamics, closed system. Okay, guys, equal what? Somebody tell me what is this? Equal what? This input minus out equal what? A change in energy within a system, which is M2 U2 plus G V2 square over 2. Everything is 2. GZ2 minus M1 U1 plus V1 square over 2 plus GZ1. So state 2 here. This is state 2. U2 internal energy. V2 velocity 2. GZ2. Can you see, guys? Can you hear that, guys? I'm talking about the show. Anupam. Anupam. Can you hear the show, guys? Not me.
Yeah, looks like it's a pretty entertaining one.
Not me, not me. I swear, not me.
That's a good show.
No, it's okay. You can like that one. It's one of my favorites.
Really? But I like you more. Anyway, so M2 equal U2 plus V2 square over 2 plus G2. Guys, we have with there. Please focus, please. So M2 is the mass at state 2. U2 internal energy, specific internal energy at state 2. V2 square over 2 is kinetic energy, specific energy at state 2. GZ2 potential energy at state 2 minus M1 mass at state 1 times U1 is specific energy at state 1. V1 square over 2 is kinetic energy or specific kinetic energy at state 1, and the same for potential energy at state 1. Here we have enthalpy because something is moving in or out. We have enthalpy here or here. For inlet and outlet, we have enthalpy. Enthalpy. It's U plus PV, usually. For the system, we only have internal energies. We have internal energies, U and U. Okay? Okay, guys? Guys, you want to hear a show or me? Guys, are you here? Make it loud and palm so they can hear it, or maybe. So M2, U2, M1, U1. This is, for example, if you put everything input 0 or output 0, and there is no this and this and this and this, you will see this equation. Okay, guys? What else we have in the system? What we can add to this equation? Two things we can add. Heat and work. We can add what? Heat. Take positive sign or negative sign. If it's addition, positive. So we say Q12 minus W12 plus this plus minus this. So this is the first of thermodynamics open system. Heat addition minus work plus some energy in minus some energy out equals a change in the system energy. So energy input, for example, have Q. Energy output, for example, have W. So W, by definition, it's positive if it's work done by the system. Q is positive if it's heat addition. Heat addition to the system. This is a positive sign, the same as first law. So if this is 0, this is 0, Q minus W equals delta U. Correct? So read it with me. Read it with me. Read with me, guys. Q minus W plus sigma energy in minus sigma energy out equals energy 2, state 2 minus energy state 1. Make sense? Does it make sense for you guys?
Yeah.
Where is the lecture? It's here. It's here. Lecture is here. I forgot. So this is called the first law of thermodynamics for an open system. It has a lot of special cases, beautiful special cases, a lot of application. Okay, guys? Maybe in the midterm, I just ask you, reduce this formula to just first law of thermodynamics for closed system. What you're gonna do? You're gonna say, there is no input. There is no mass can cross. These are going against guy gun. There is no kinetic energy, potential energy for closed system. So it will remain Q minus W equal U2 minus U1. That's it. Yeah, and mass is the same. Take mass common factor between M2U2, M1 U1. Correct? If you go back to the lecture 7, we almost done to 7.5. I add a lot of details, a lot of notes. Please read the lectures. Okay, guys? Guys, as of here, is everything is fine?
Yes.
Yeah.
In the review, I'm gonna continue this lecture in the review. Like when I do the review, I'll do this. I'm gonna first review chapter 1, chapter 2, 3, and 4, and section 5 and 1. 5.1, 5.2. Then I will solve a sample midterm. Last year midterm, I will solve it back in the review. Then I'll give the end of this lecture to be moving without any lag. Okay?
Can you please post the example midterm this weekend?
Sure. I'm gonna post it.
Like
Let's
today.
say today. I was gonna solve. Hopefully today I will, because I'm busy these days. I'm gonna post it as soon as possible. The sample. Then I will solve it Monday, so you'll have it. So I'm gonna first review, then solve the midterm for you. Next, the midterm is next week. I wish that all of you make sure that you can solve the quizzes, lecture problems, quizzes, lecture problems, homeworks. Make sure these three: quizzes, lecture problems, quizzes. Everything I solve in the lecture is important. Okay? Now, do you want to hear the show?
Yes.
No. The lecture is over.
Oh.
Okay. I miss you guys. Yeah, next week. Okay, guys?
Thank you, Professor.
I'm sorry for
Have a good
any
weekend.
miscommunication in the online. I like that's why I don't like online classes. But anyway, hopefully soon they will put more facilities in the school, so we can give it in the school in much better quality. Okay, guys?
Okay.
Thank you.
Any question, guys? Please don't hesitate to send me an email anytime. Anytime, send an email to me if you have any question. Yeah, good. Have a good day, guys.
You too. Thank you.
Thank you. Have a good one, Professor.
Yeah, you always have lecture notes. I always post it in advance. So, for example, today or tomorrow, I will post the following 2 or 3 lectures. So you need to read them in advance with the same problem will follow. This one of the people was asking.
Oh, Professor, are you gonna put the quiz solutions? I know you went over them after.
Yeah,
after
it's our posted. Yeah, actually the TA also asked me. I will post it for you guys. I'm sorry.
Cool. Thank you, Professor. You have a good one.
It's just very simple. I already solved it in the quiz, but
Yeah.
okay, I'm gonna do it. I'm gonna do. No worries. No worries.
Cool.
No
Thank
worries,
you.
guys. We are
Have a
here
good one,
to help
Professor.
you. Okay, guys.